In part 1 of this film, you saw how to conduct a survey for noise levels, for heat stress, and for light. In this part, we deal with the equipment and techniques for measuring gases and various airborne contaminants. And we'll also show how you measure the effectiveness of ventilation and exhaust systems. The recognition phase begins as usual, with some preparation work in your own office. For each place you'll be surveying, you go through the file folder to learn about the work processes, hazardous operations and materials, protective equipment that is supposed to be in use, and so on. And you make note of control recommendations from the most recent inspection, so you can check on whether the problems have been corrected. A facility such as a motor pool can take considerable time for a careful and thorough survey. On the preliminary survey, you determine what kinds of measurements and sampling will be required. You gather all the general information, such as details on any significant changes in operations, equipment, or materials. The survey at the motor pool, for example, was originally requested because of the recent installation of a vapor degreaser. The handling of chemicals can present potential hazards. During the preliminary survey at this lab, you find out if the supervisor and the workers know what protective equipment is required and if they use it. And you collect other data you'll need. Reviewing the data you've gathered, you then select the instruments you'll need to evaluate the work environments and prepare them for use. We'll go through the checkout procedures for these common instruments. First, the anemometer, or air velocity meter. To adjust the calibration, select the velocity and static pressure mode and the 100 to 1000 scale. Then hold down the check button. The needle should swing and stop exactly over the red calibration mark. If it doesn't, correct it with the current adjustment knob, the one associated with velocity and static pressure mode. From time to time, you should also remove the batteries and test them using the built-in tester. The anemometer is provided with a system that protects the meter while the instrument is being carried. Mount the probe in its clips so that the button, the meter shunt switch, is pushed down. Then release the selector buttons and make sure they're all up. The instrument can now safely be carried without damaging the meter. The air at both the motor pool and the laboratory will have to be checked for presence of hazardous concentrations of gases and vapors. One instrument for doing this is the carbon monoxide analyzer. In the instruction manual for the instrument is a list of interfering gases that can cause incorrect readings. From your preliminary survey, you should know whether any of these can be expected at the survey location. The A position of the selector switch is used to check the instrument batteries. The B position checks a separate battery that runs the pump. Each position should give a reading at or beyond the battery line. Next, switch to the 0 position and let the instrument warm up for 3 to 5 minutes before continuing. When the needle has settled down, use the 0 adjust screw to get the correct meter 0 position. Now turn the meter on. And you're ready to adjust the flow rate. The rate at which air or gas is being pumped through the unit is shown by the flow meter. Adjust the rate to 1.5 liters per minute. The next step is the span check. This is a calibration procedure using a small quantity of the gas you'll be sampling for. The gas sample is transferred into a plastic bag. Never run it directly from cylinder to intake. You might ruin the instrument. Stamped on the cylinder is an accurate measure of the concentration of this particular gas, given in parts per million. Attach the plastic bag to the intake port of the analyzer. What you now do is adjust the meter so it reads exactly the value shown on the cylinder. With the flow rate adjusted and the calibration set, the analyzer is ready for use. These adjustments should be made each day you use the instrument, because the settings may drift. To sample the vapors from the vapor degreaser at the motor pool, your survey team will be using this gas sampling pump and these detector tubes. Detector tubes are available for sampling many different types of gases and vapors. Make sure you have the correct type. Also, be sure the tubes haven't reached the shelf life expiration date. Check the pump by doing a field leakage test. Insert a detector tube without breaking the ends. Pull out the piston until it locks and wait for 2 minutes. At the end of that time, let the piston back in gently. The amount of air that's leaked in can be estimated by the reading on the pump handle. If the reading is greater than 5 cc's, the pump probably needs nothing more than a little lubrication. You should also periodically check the volume of the pump. To do this, you make up a solution of half water, half liquid detergent. To prepare the pump for the volume test, break off both ends of a detector tube and insert the detector tube into the pump. The next step is to thoroughly coat the inside of a 100 milliliter burette with the detergent and water solution. When you touch the burette to the surface of the solution, a soap film forms at the mouth. Connect the burette to the pump assembly and pull a full stroke on the handle. The distance that the soap bubble travels through the burette indicates the volume of the pump. The volume should be 100 milliliters. You'll be using these personal air sampling pumps to sample for certain air contaminants at the motor pool. Along with them, you need the appropriate collection media for each kind of contaminant to be sampled. And for the motor pool welder, you'll also need the specially prepared welder's helmet. It's convenient to use copies of the air sampling data form for recording your readings during the survey. The flow rate of each pump needs to be determined, depending on what you'll be sampling for. In the Industrial Hygiene Evaluation Guide, you'll find the correct rate and minimum sampling time for each contaminant. As an example, a solvent used in a vapor degreaser is methyl chloroform. You sample for it with a charcoal tube at a flow rate of 1 to 2 liters per minute, collecting a minimum 10-liter sample. So you want to adjust one of the pumps for a flow rate of 1 to 2 liters per minute when sampling with a charcoal tube. To determine that adjustment, you'll first need to calibrate the flow rate of the pump. Insert a charcoal tube in line between the pump and a 1-liter burette. Turn on the pump and adjust it to the initial ball setting. You need to determine the flow rate over a range of ball settings, using a method similar to the one shown earlier. The time it takes the soap bubble to travel the length of the burette is used to figure the flow rate for each different ball setting. Enter the corresponding flow rate for each ball setting on the data form. You should maintain a separate calibration chart for each pump. Before every survey, each air pump should be recalibrated and a new flow rate chart prepared. You can also calibrate the pumps with a wet test meter, which gives a direct reading of the air volume pumped in a given length of time. Another instrument to be calibrated is the one you'll be using at the laboratory for detecting and measuring mercury vapor. To check the battery, switch to the V or voltage position. The needle should move above the red area. The instrument requires a long warm-up period, 10 to 20 minutes. When it's warmed up and with the probe connected, you can zero the meter. Set the air control knob to the filtered air position and the function switch to 1.0. Now loosen the locking clutch on the zero adjust knob and turn the knob as required. If you're unable to zero the meter that way, larger corrections can be made with the course adjust screw. Use the zero adjust knob for the fine adjustment. Then, switch to the 0.2 scale and zero the meter again. Secure the locking clutch and then shift to the ambient air setting to take a reading. It's recommended that you check the response of the instrument with a sample of mercury, if you have some available. That completes the preparation of the instruments. Your team is ready to begin the surveys. At a motor pool, the presence of air contaminants from vehicle exhaust is always a concern. So, one thing you want to know is how good is the ventilation system? For instance, how much air is it moving? You find out with the anemometer. Select velocity and the appropriate scale and take a centerline air velocity measurement. Turn the probe so the red dot is against the airstream, and with the probe 90 degrees to the airflow, hold the probe very still. You need to take air velocity readings at each outlet in the motor pool. This data you will later convert to volume of air moved. For an actual measurement of the carbon monoxide levels, The CO analyzer gives direct and accurate readings. Place it close to the worker. Turn it on. And in a few moments, you can read the concentration in parts per million from the scale. For long-term sampling, it's important that you connect the humidity control bottle filled with distilled water in the intake line. This will keep the sensor material in the analyzer from drying out. In the brake relining area, you want to measure the worker's exposure to asbestos fibers. To do this, you need to collect air contaminant samples from the immediate vicinity of the worker over a set period of time. Your air sampling equipment will be attached directly to the worker. In this way, accurate samples of the air that he is breathing can be obtained, regardless of where his work is performed. An open-faced filter cassette traps any asbestos fibers that may be in the air. The air sampling pump will draw air through the filter. Record the starting time, and when you're done, the stop time. In between, check the flow rate on the pump periodically. Most welders know that welding fumes can be toxic. They know they should use a local exhaust ventilator hood for their own protection. You want to see whether he is using one, whether he's using it correctly, and whether it is moving enough air to be effective. You'll be able to visually check how the ventilation hood is performing with the aid of a ventilation smoke tube. The actual air velocity you measure with the anemometer in the usual manner. Measure and record the air velocity at various distances from the hood opening and, most importantly, at the area where the welding actually occurs. And how about the air that the welder is breathing? Once again, you need to attach your sampling equipment directly to the worker to obtain air samples over a measured period of time. The special welding helmet has the filters already mounted in a manner to obtain air samples from within the helmet, the air that the welder is actually breathing. Again, air sampling pumps are used to draw the air through the filters. The Industrial Hygiene Evaluation Guide tells you what type filter to use and how long to sample for the different types of welding fumes. The solvent used in this vapor degreaser is methyl chloroform. It's used for cleaning dirt and grease off metal parts, and it can be dangerous. Detector tubes are useful for initial sampling. They give a good indication of whether more accurate sampling is called for. While waiting to see if you get a reading, you should check the worker's knowledge of the potential hazards and the necessary safety practices. A positive reading causes a color change or staining inside the tube. Check the detector tube instruction sheet for detailed information. You'll need to take several readings during various stages of the operation. Be sure to change to fresh detector tubes between each reading. It is especially important to take readings during the raising and lowering of the parts basket. It's during this phase of the operation when vapors are most likely to escape from the tank. At the end of the predetermined time periods, stop each of the air sampling pumps and recover the filter cassettes. You will send these into the lab for analysis. Be sure to include your data sheet with each. The health and safety of laboratory personnel depends heavily on observation of safety procedures and proper functioning of safety equipment. You can measure the effectiveness of the lab hoods with the anemometer. Again, be sure to hold the probe at a 90-degree angle to the airflow, with the red dot against the air stream. Do not take readings close to the edges of the hood. You take readings across the face of the lab hood and average them. Another important check of the lab hoods is done with ventilation smoke tubes. They show whether the hood is exhausting the air properly, or whether there is some blowback into the room. When using these smoke tubes, be careful not to inhale any of the smoke or get any on your clothes. Wherever mercury is used, a careful survey with the mercury vapor detector is very important. Allow 10 to 20 minutes warm-up time. With the detector on the 1.0 scale, recheck the zero adjustment before starting. Then shift to the ambient air position to begin your survey. Check specific work areas where mercury is used. Move the mercury vapor detector slowly and observe the meter for an upscale deflection. Certain gases and vapors can interfere and cause erroneous readings with the mercury vapor detector. From your preliminary survey, you should know whether any of these can be expected. When you detect mercury vapor, allow the needle to stabilize and take a reading. Then shift to filtered air. Wait for the needle to drop to 0. Reset the zero adjustment if necessary. Shift back to ambient air and take another reading. After locating the source of the vapor, clear the instrument by shifting back to the filtered air position. That completes the procedures required for this particular lab. A large part of the job still lies ahead. Analyzing the data, doing the necessary calculations, comparing the contaminant levels you found with the standards, and, of course, the important control step, making recommendations to reduce or eliminate the hazards. Each installation you survey is unique, presenting its own unique challenges. Industrial hygiene surveying can be deceptive. It may look easy, but as you learn more about it, you'll find it is involved, complex, and demanding. You play an important role in helping to protect the health and safety of many people. To fulfill that responsibility, there is much to know and always more to be learned. Reviewing the data you've gathered, you then select the instruments you'll need to evaluate the work environments and prepare them for use. We'll go through the checkout procedures for these common instruments. First, the anemometer, or air velocity meter. To adjust the calibration, select the velocity and static pressure mode and the 100 to 1000 scale. Then hold down the check button. In this part, we deal with the equipment and techniques for measuring gases and various airborne contaminants. And we'll also show how you measure the effectiveness of ventilation and exhaust systems. The recognition phase begins as usual, with some preparation work in your own office. For each place you'll be surveying, you go through the file folder to learn about the work processes, hazardous operations and materials, protective equipment that is supposed to be in use, and so on. Changes in operations, equipment, or materials. The survey at the motor pool, for example, was originally requested because of the recent installation of a vapor degreaser. The handling of chemicals can present potential hazards. During the preliminary survey at this lab, you find out if the supervisor and the workers know what protective equipment is required and if they use it. And you collect other data you'll need. And you make note of control recommendations from the most recent inspection, so you can check on whether the problems have been corrected. A facility such as a motor pool can take considerable time for a careful and thorough survey. On the preliminary survey, you determine what kinds of measurements and sampling will be required. You gather all the general information, such as details on any significant In part 1 of this film, you saw how to conduct a survey for noise levels, for heat stress, and for light.